Hello everybody and welcome to MI212. Mark Gastinga here again, and we are going to move on to our next topic in the series. That's on the topic of population PK/PD modeling. Today we're going to essentially do what's a review, and it'll lay the foundation for the following few weeks, where we're going to get into some advanced PK/PD modeling topics. But just to make sure that we're all on the same page, we're going to review some of the basics of direct and indirect type pharmacokinetic pharmacodynamic models. So we're now on Chapter 5. We'll call this Advanced PK/PD Modeling Topics, Part 1. And as I mentioned, this will be a review for some of you. If you've taken the MI210 class, we covered most of this material there. We'll dig into a little more detail in some of these models, as well as at the end talk about models for circadian baseline data. But most of this is pretty basic. We're talking about describing responses as a function of concentration, whether they're observed concentrations, such as you might see in a $pred type model, or model predicted, where you have a full PK/PD model link. And then there's a variety of variations on that theme. And then you can have linked models that are direct or indirect, and we'll discuss both of those situations with a variety of different ways to model indirect relationships. Before we get into the models, I was going to cover a few topics that come up in this discussion. A little bit about data design issues, individual versus population concentration responses, reviewing strategies for simultaneous versus sequential fits, and so on. Okay, so why do we model PK/PD, or exposure response? One is to explain, understand, and control the dose concentration response relationship, explaining variability in that relationship, as well as now we're getting into something more useful, where we can provide a framework for clinical trial simulations where we're doing something more than a pharmacokinetic outcome as a dependent variable. And then potentially providing supportive clinical efficacy as that second requirement in registration trials. Exposure response could play a role in that relationship too. There are many reasons for modeling exposure and response. I think for most of this audience, they should be obvious. But I've listed several references at the end of this chapter, and you'll be able to read more. Now, when we talk about the design for population PK/PD, really the key here is to obtain a concentration response relationship within the individual. This is something that's often overlooked, and it's assumed that if you have concentration data and you have response data, that you can go ahead and develop a useful PK/PD model. And that's not always the case. The design is quite important here. And in particular, when you only have one endpoint per individual, you don't have an individual concentration response relationship. You have really what's a pooling of a population effect. And that can be misleading in some cases. Another key point here is that if we're building structural models for pharmacokinetics, it's not necessary to match concentration and responses in time. We can, at least not the observed cases, we can make model predictions at any time. Sparse sampling is possible, but you often want to see multiple concentration response observations for each subject so that we can obtain that individual specific effect, the individual specific parameters for the concentration response. Otherwise, again, you're just relying on that relationship that the population cloud of data contains and hoping to apply that to the individual. That's a big assumption. In addition, aiming for a variety of exposure response conditions is important. So we might talk about single dose PK/PD as well as multiple dose, maybe looking at response both when concentrations are rising and falling, or maybe rising at different rates. Looking at a range of doses. I mean, to really understand PK/PD relationships, you need to probe the system from multiple angles under a variety of conditions. In typical drug development trials, we often do not have this sort of luxury. We're usually stuck with some design that's been implemented for a different purpose, not for understanding PK/PD relationships, but really for understanding some proof of concept or some dose response, or even a confirmatory efficacy type objective. And just reviewing a few of the models that we typically use to relate concentration and response, and this is, I'm sure, obvious to all of you. Most of these relationships arise from receptor occupancy, or the theory of mass balance, where at equilibrium we understand that there's some binding between drug and target, and that elicits some response. And so most of the models are derived from that sort of a binding type expression. There's actually a typo in this one here. Sorry about that. This is the sigmoid Emacs model, where n is what's known as the Hill coefficient, but it's missing here from the EC50 term. I'll go back and fix that and repost the notes. But this expression is actually derived from the cooperative binding of oxygen and hemoglobin. That's where the Hill coefficient comes from. But that same sort of binding isotherm can be used to describe drug target binding, and as well, more empirically, just the shape of exposure response relationships. And so that's really the for a single drug at a single receptor, that's the basic case. And then all of these additional models are special cases here, where we might have a truncated sigmoid Emacs model that has this sort of shape with the Hill coefficient, or a linear model, which again is truncated but assuming a Hill coefficient of 1, or maybe a log linear relationship, where in this model parameters are Emax and EC50 for the full sigmoid Emacs. E0 is a baseline parameter. Emax is the maximum effect of the drug, and EC50 is the concentration that produces half of that maximal effect. In simpler cases, we still have the E0, but the slope parameter is represents the ratio of Emax to EC50, usually occurring when concentrations are much below EC50. So these are things that I'm sure you're familiar with, and here's a $pred example in NM code. There's no PredBP library for pharmacodynamic models, but we do have $pred where the user can define any relationship they're interested in. This one here demonstrates a simple data set that has an ID, a dependent variable, which is the pharmacodynamic observation, and a concentration. And the DV, again, pharmacodynamics, concentration is the independent variable, and so we construct the model where concentration is the predictor. So define an Emax and an EC50 here with some typical value fixed effect and some inter-individual random effect, and then some effect where effect is defined as an Emax model dependent upon observed concentrations here. You'll notice that Const is observed in the data set, and that's what's used in this expression. So this is a direct pharmacodynamic model, assuming a direct link to observed concentrations. And we'll specify an additive residual error here, and so on. So that's pretty straightforward. This is about as basic as you can get with an NM-tran control stream, but this is a direct pharmacodynamic model based on observed concentrations. Well, a few other things to think about here. We're going to go a little bit further now and use the PK model that we might have developed and link PK-PD relationships. And all of these that are bulleted in this list we'll address today. Direct links, effect compartments, time-dependent models, indirect pharmacodynamic response models. All of these involve some sort of link of a PK model with a pharmacodynamic model. They can also be applied to underlie other endpoints too. So you could have this direct relationship between observed concentration and maybe an unobserved continuous response, but it might be linked to some categorical outcome. I just wanted to point that out, that these direct type links can also be used, or these link models can also be used to model pharmacodynamic endpoints that are categorical in nature. Now, so sometimes there's a discussion, if you have observed data, why build the PK model? Why use model predicted? And so this is a judgment call, and there's a few factors that would allow you to make that decision. But you've got to weigh those factors. Number one, the nice thing about using the model is that a pharmacokinetic model allows you to make predictions of concentrations at all of the pharmacodynamic observation times. So if the study design is one that doesn't have matched pairs in time, it doesn't cause a problem. You can always use the model to predict the concentration in that individual at that particular time point. The advantage here is you have no dropped pharmacodynamic data points due to a lack of a matching concentration observation. Sometimes, that we make a little bit of a stretch there, and if they're not exactly matching, you might take the nearest concentration, which could be, a few minutes, maybe a few hours away. Depending upon how the concentration time relationship is changing, how rapidly the peak to trough fluctuation changes over time, this may or may not be important. But the nice thing about a model is that you always have the ability to make a prediction at each one of the PD observation times. Probably one of the most valuable reasons for using model predicted is because the pharmacokinetic model provides a prediction of concentrations that would be individual specific, but it eliminates the residual error from that prediction. So it eliminates the noise in the concentration data. Now, assuming that it's an unbiased fit, that's a useful thing. And in fact, when you're looking at any regression model, one of the assumptions is always that the predictor variable, and so for a PD model, that's the concentration is the predictor of response. The predictor variable is assumed to be known without error or with much less error than the response variable. And so here's one where using model predicted values might be important. This happens pretty frequently where we have PK observations matched over time with PD observations, and it might be that your PK endpoint is more variable than the PD. So you have to weigh that factor. And what would happen, of course, is if the PK variability is too large, or if the variability in the predictor variable is too large, it actually ends up blunting the response or shifting the apparent response to a null relationship when there might really be one there. So this is a good argument for using model predicted concentrations. Another practical thing is if you're building a PK model and a direct relationship isn't adequate, then it's easy to extend that model to a more complex one, like an effect compartment model. But the last one, of course, is that both the PK and PD predictions are going to be dependent upon the accuracy of the PK model. And so if you have a PK model that's not a very good descriptor of the data, or deficient in some parts of the concentration response relationship, it may be problematic with respect to predicting response. And unless you can improve that, that might be a reason for using observed concentrations instead of model predicted. Another consideration is what kind of concentrations should we use? Well, we talk about building population PK models, and that's a large endeavor, long process where we build models for covariate effects, evaluate random effects distributions, perform predictive checks, and so on. But sometimes when we really just want to understand the exposure-response relationship, we can shortcut all of that by just moving to a solid base model on the pharmacokinetic side and using some conditional estimation method to determine the individual concentration predictions. And so that can be a useful shortcut when your goal here is to predict concentrations for the current data set only, so we're not really concerned about understanding the effect of covariates to predict into a future data set. Understanding the factors of PK variability is not a goal. And of course, where the individual concentration prediction provides a good fit to the PK data. If you're in those situations, it might be suitable to just build a simple PK model, estimate individual predicted exposures, and then run the PK-PD relationship. Okay, well, there's some different strategies for modeling PK-PD. We're going to get into differences between sequential and simultaneous fits now. And I'll describe a few. There have been a few publications on this topic. But essentially, here's the common strategies. Here are the common strategies that you might want to pursue. So one that's pretty useful is a sequential fit, and I'll call it sequential fit 1, where you first model the pharmacokinetics in a population and fix the parameters to the final individual estimates of PK parameters. And then we model PD conditioned on the fixed individual PK parameters. You only need to include PD data in this data set. So that's a two-step process where we're using conditional estimation of PK and then carrying those parameter estimates into the data set actually of the PD model, and then making predictions of PD or estimating the PD parameters conditioned on those individual pharmacokinetic parameter estimates. In sequential fit 2, we could take a similar approach, but we model the PK first and fix the parameters to the final population estimates rather than to the individual estimates. And then we model the PK-PD given fixed population PK parameters. This is usually part of the process that we undergo if we're moving to a simultaneous fit. You'll start with this sequential fit at the population level just to get some good initial estimates of both the PK and PD, and then go to the full simultaneous fit where PK and PD are estimated simultaneously, maybe using the sequential fit 2 here as your initial estimates, and allow all the parameters to be estimated. And this has been called the gold standard, but there are some caveats there. Here are some reasons why you might want to use sequential fits instead of simultaneous. Well, first of all, if the simultaneous fit is conducted in a method that doesn't allow conditional estimation of individual random effects, then we're essentially building a PD model off of population mean PK parameters. So anytime you can't get one of the conditional estimation methods to run, either because of convergence difficulties or time constraints, simultaneous fits are not the best way to go. In that case, I would suggest using sequential fit 1, where you can propagate that individual specific PK information into the determination of the PD parameters. So that's one reason why you might not want to use a simultaneous fit. However, the simultaneous fit does give you other advantages in that you now have estimation of inter-individual random effects across PK and PD parameters at the same time, And we can actually model correlation in those parameters across PK and PD as a potential source of or a potential descriptor of the variability, and it can happen that way, particularly with target-mediated drug disposition mechanisms, where PK parameters and inter-individual difference in those are correlated with PD endpoints and PD parameters. So only a simultaneous fit allows you to do that. Anyway, I think that a good starting point is something like the sequential fit number one, which is less computationally intensive than a simultaneous and produces results that are pretty good. And certainly, if conditional estimation is not possible on the simultaneous fit, you're going to want to use the sequential fit. Okay, so those are just a few thoughts, a few comments. There have been lots of discussions on these types of things in the different web forums and in publications over the years. But these are some things to think about as you're modeling. Next, we're going to really just talk about implementation of these models and what types of models are useful for different types of data. But I'll take a moment and I'll answer a few questions if there are any. There's a comment here that at times I prefer sequential fits if the PK is measured much more precisely than the PD. Example, PD is heart rate or FEV1. Can that be accommodated in a simultaneous fit? What I'm getting from the question here is when you're saying PK is more precisely measured than PD, meaning that there's a different precision to the analytical method or the measurement tool, and you don't have to do that sequentially in order to accommodate that difference. And we'll see as we go to simultaneous fits in the class examples, we can actually specify different precisions or different residual variance models for the different endpoints. So if PK is much more precisely defined, well, we'll weight it accordingly and allow for a different residual error for PK than you might for pharmacodynamics. So that's not a problem, and I don't see any reason why a simultaneous fit could not accommodate that. Okay, any other questions? One more question here. If the PK model is missing Cmax, should I use concentration? I guess you're saying, should I use observed concentration? Well, that's one case where you might consider it. So if you have a pharmacokinetic model that is biased with respect to part of the concentration time curve, and if that part of the concentration time curve, for example, Cmax, is important from your pharmacodynamic modeling point of view, then yeah, maybe you should use observed concentrations if you have them. It depends on how poorly the model is describing the data. But if there's significant misfit between the predictions and the observed concentrations, you might be better off to use the observed data if you have them, and if the effects are direct. I'll talk about another strategy too, where the another strategy where the observed data can be used for indirect relationships. That's called a semi-parametric method, and we'll discuss that in a few minutes. Okay, any more questions? Let's move on then. Implementation of PK-PD models. So these are linked models in NONMEM. So the direct linked models are easy. Those we can just link the PK predictions to pharmacodynamic predictions through the error block of any of the advan routines. Effect compartment models and this tolerance model we'll talk about. Models that are not direct or have some sort of kinetic component, some additional kinetic component to them, they can be modeled through the analytical advans or the general models as well, but we've got to accommodate an additional compartment for that. And of course, indirect pharmacodynamic response models require differential equations, and those are the advans 6, 8, 9, and 13, which we've used in this course in the past. Let's jump to a direct PK/PD model. So here's a PK system where you have a depot, compartment 1, a central compartment, compartment 2, so probably oral dosing, and then elimination from the central compartment. Effect now is a function of concentration in compartment 2. Whatever that function is, it's some pharmacodynamic model. So we want to link PK/PD here. So the PK system model is described above. The PD model is pretty simple here, just some general function of concentration in the central compartment. How do we do that? Well, let's look at two different ways of structuring the data set. So let's look at a simultaneous PK/PD fit first. If we're doing simultaneous PK/PD data, just like when we do simultaneous estimation of parent and metabolite data and urine data, for example, we have a single DV column. What's necessary, though, is that we carry with that a type indicator, which would indicate the type of dependent variable. So 1 might be PK, 0 might be PD. The rest of the data set is just about the same as always. We have an ID, time, amount, and this is assuming we're modeling pharmacokinetics here, so this follows the typical pred-PP requirements. Time 0, we have an amount indicator, and then we have matched pairs of observations in some cases. So at time 2, we have both a PK and a PD, but then at time 4, we have a PK, time 6, we have a PK, and time 7, we have a PD, so they're not matched pairs. However, with this construct, we can accommodate all of the data, and we don't have to throw away all of these data points because they're not matched. So that's the construct for a simultaneous PK/PD model. I did not include the L2 data item in any of the examples we're talking about today, but we talked about that last week, and that could certainly be used here when you have a multivariate observation. So in this example here, where we have time 2 of both a PK and PD taken at the same time, we could assume that residual error might be correlated between those two components of the multivariate observation, and we might want to indicate that with an L2 data item, which would be the same for both of those records, and then estimate the correlation in the sigma block. Now here's the strategy if we want to build that sequential fit. So we've already done the PK modeling here, and using a conditional estimation method, generated individual PK parameters, and I've labeled them here clearance I, or clearance for the individual, volume for the individual, and Ka for the individual, and you'll see those here listed in the data set for each individual, and they're constant throughout each individual, of course. These are not recognized by NMTram, but you'll see how we take advantage of that in the control stream. The other thing that's different with this model now is we still have the dosing records, because we're going to advance the compartmental amounts and concentrations in the PK system according to the dosing history. But the observations now for PK are not important because we've estimated the PK parameters. What we are going to include in the DV column is the pharmacodynamic observations. Okay, so let's look at the code for each one of those. First, the simultaneous PK/PD model for a direct pharmacodynamic effect. We have a data set similar to what we just described. Subroutine here, we're going to use advan 2 trans 2. So this is a one compartment model with first order absorption, parameterized in terms of microconstants. In terms of clearance and volume, physiologic parameters, trans 2. And then you'll see PK here, $PK is the typical $PK block where we define Ka, clearance and volume. We're going to be estimating PK parameters. So the scale for the observation of PK is V, the central compartment volume. But then we're also going to make a prediction of pharmacodynamics. So in the error block, and it's not required that we define these in the error block, but I've done so, we define the PD model parameters. And here we're going to simply describe a basic Emacs model with a Hill coefficient assumed to be 1. So we have an Emacs parameter with some fixed and random component, an EC50, and an E0, a baseline. And the effect that we would predict is equal to the baseline plus Emacs times F divided by the quantity EC50 plus F. And then that whole thing is our model prediction with some residual error here, error 2, we're calling it. We also have a prediction for concentration, which is equal to F, or the predicted concentration from the PrEP-PP subroutine, plus this proportional error. Now notice that the errors are different. We have a proportional relationship for concentration, and it's based on the subscripted error 1. So this is going to be summarized by a variance in sigma 1,1. And the PD endpoint is additive in its residual, and that residual variance is going to be in sigma 2,2. So two distinct residual error models here. And this gets at the point that was raised earlier about accommodating PK measurements that are more precisely estimated. You could do that by allowing for different residual errors. And then simply the prediction then, the observed data is equal to the prediction, which is conditioned on the type variable. So if type is 1, that's PK, and concentration comes through. If type is 0, that's PD, and effect is the prediction. So very similar to the way we handled the parent-metabolite models and so on. We use these indicator variables to switch the prediction. Okay, I've got a question here on this one I noticed. Why is concentration used for effect, including error, instead of F? Why is constant? I'm not sure where that's coming from. Concentration here, this line here that says const equals F plus error, that's the PK prediction and the residual error for PK. This residual error in PK is not propagated into the PD. PD is simply based on F, and F here is the predicted concentration for the compartment of interest, the default observation compartment, that comes out of the PrEP-PP routine. So these are two separate predictions. We have an effect prediction and we have a concentration prediction. Okay. Now let's look at how we would change that if we were going to run a sequential model. The data set now includes, as I showed you above, 3 new columns: clearance for the individual, volume, and Ka for the individual. So these are individual specific estimated PK parameters from some conditional estimation method in the PK modeling. They're plugged in now from the table output in the first PK run. You plug these now in as input in the PD component of the sequential fit. We're going to use the same structural model. It's a PK structural model, but the PK block now, you'll see all the parameters are fixed. Ka is equal to the individual, clearance is equal to the individual estimated, and volume is equal to the individual estimate. So we're not estimating any pharmacokinetic parameters in this model. We're using them to predict concentrations, though, at the appropriate times, so that when we get to the error block and try to estimate the effect parameters, Emacs, EC50, and E0, we have an appropriate PK prediction based on the individual specific PK model. The rest of the structure is the same here, except we have no concentration prediction. All we have is an effect prediction, and that effect is equal to this Emacs model, which is a function of F, again, F being the predicted concentration in the default observation compartment. We have residual error, that's it. So there's only one dependent variable in this model, and that's the pharmacodynamics. It's not a multivariate model. So that's another reason why you might, another potential shortcoming of the sequential approach is that you can't model that level 2 correlation, or the correlation of the residual random effects, if that's important. But generally speaking, this is a pretty rapid way to prototype PK/PD models, and works pretty effectively. Now we'll switch gears to indirect models, and one of the ways that we model indirect relationships is using an effect compartment model. And this model here that we're looking at is really looks like a two-compartment system model, but we have a one-compartment PK component, a depot, compartment 1, central compartment, an absorption rate constant, and then elimination from the central compartment. And then this peripheral compartment is not necessarily the peripheral compartment of a two-compartment PK system, but it's actually an effect compartment which allows us to model an apparent disequilibrium between the effect time course and the concentration time course. Oftentimes, this is related to differences in equilibrium of sampling pools versus effect sites, or maybe the slower transduction of the response relative to the time course of concentration. But it's oftentimes needed, and I'm sure that most of you in this group are familiar with those reasons. The way we model this here is as an additional kinetic component to the system, where K2E is some negligible transfer, some first-order transfer from the central compartment to the effect compartment. And KE0 is an estimated first-order rate constant that describes the equilibration half-life for the effect compartment. Now, if you look carefully at this, you'll see this looks a lot like the model described in ADVAN4. ADVAN4 is a two-compartment disposition with first-order absorption. The one thing that's different with ADVAN4 is that the return rate constant is not an exit rate constant here from compartment 3, but it's a K32. It's returning from 3 to 2. But we can take advantage of that model structure since we have an analytical solution for those compartmental amounts, and we can take advantage of that quicker runtime by using that with a slight trick to describe an effect compartment model. Alternatively, you could code up this particular model using the general linear models in ADVANS 5 and 7, or differential equations 6, 8, and 9, and of course 13 as well. So here's what the dataset looks like now for an effect compartment model. Everything is the same as before, except the same as the simultaneous fit we did for the direct relationship, but now we have a CMT data item. Dosing record again into compartment 1, and now we have type and compartment, which are telling us different things. Compartment 2 here is the central compartment, and that's a PK observation. Compartment 3 is a PD observation. And actually we could key off of compartment in this particular model because compartment changes when type changes. But you'll see later on that there are times when that connection is not always there, and it's useful to have both indicators. But what we're going to do is identify that the PD observations are coming from that peripheral compartment and the PK observations from the central. In fact, I'm going to back up and just make one more suggestion to your modeling strategy. Before you jump to this model, if there's any chance that you have a multi-compartmental kinetic system, so a 2-compartment or 3-compartment disposition, before building an effect compartment to relate to responses, you might want to just look at the predicted concentrations in the true peripheral compartments of a multi-compartment PK system. In fact, that was the first example that led us to think about effect compartments. Is John Wagner had published some work on LSD where we were looking at peripheral compartment concentrations related to response. If it's a one-compartment system, though, and you still have that kinetic lag, then you need to introduce this additional effect compartment. Okay, let's see. I was going to show you the code first, and then I'll answer questions. So here's our effect compartment model. We have type and CMT in the data set. Compartments 1 is the gut, 2 is the central, 3 is the effect compartment. So we're going to use Advan 4 and Trans 3. Trans 3 because we're not going to define all of the intercompartmental clearances and so on. Did I say Trans 3? I said Trans 1 because we're not going to define all of the intercompartmental clearances and volumes. We're going to define those transfers in terms of microconstants. But the PK system model is still defined in terms of a Ka clearance and a central volume. We have a Ke0, which is, remember, the first order exit rate constant describing the time course here for the effect compartment, this Ke0. We have a volume of distribution for the PK observations. That's S2 is the scale, and it's equal to the central compartment volume. And then we also set up this equality here, which just allows us to estimate effect compartment concentrations on the same scale or same magnitude range as plasma concentrations. And all we're saying is that the intercompartmental clearances are equal. So in other words, S3 times K32 equals S2 times K23. That equality allows us to interpret the effect compartment concentrations as if they were plasma concentrations. Of course, we don't know what the magnitude of the effect compartment concentrations are or the true biophase concentrations. This is just an approximation that we use to help understand that concentration response relationship. Really, all we're doing is we're estimating the shape of that relationship where we're in sort of inducing a particular concentration interpretation to the effect compartment concentration. Okay, then we're going to specify two different concentrations here, CE and CP, and remember we can use this, we can pull out the amount in compartment 3, divide it by its scale, and do the same for compartment 2. Emacs and EC50 and E0, these are all defined as we did before, but now instead of having both of these functions for concentration and effect predicted from the same concentration, now we're choosing different concentrations. So concentration is a function of CP, and effect is a function of CE. Recall two different residual errors, just like we had before, and the indicator variable to switch different types. So this is a pretty straightforward implementation of an effect compartment model. We benefit from the analytical solutions that's already present in Advan 4. And otherwise, it's quite similar to the direct relationship. The real key here is modeling that Ke0. You'll notice that I forgot to mention this, but the transfer constant from the central compartment to the effect compartment is fixed to some very small fraction of the elimination rate constant. The reason we do that is so that this transfer to the effect compartment is negligible and does not impact mass balance for the PK system. It's one of the assumptions that you need to make if you're using this analytically solved model. So even though the K32 returns back to the central compartment, it's still equivalent to the Ke0 because this mass transfer to the effect compartment is negligible, and so the transfer back is also going to be negligible. What we're doing, though, is still estimating the time course and the shape of that relationship, and this construct allows that. Okay, so now let's answer a few questions. Someone's asking about commenting on the comparison between effect compartment models and indirect models. And what I think you're talking about is indirect pharmacodynamic response models, which we'll talk about next. So I'll hold off on that. Another question. Instead of making K23 negligibly small, can I make V3 very small to keep the mass transfer to be negligible? No, that's not going to work. Because if you make this peripheral compartment small, or the effect compartment very small, it doesn't mean that the rate constant is going to be artificially small. All that might do is give you very high concentrations in the effect compartment. Now you really have to clamp down on this transfer here and make this negligible. Sorry, I lost my mouse. Go back to the questions. What happens if you fix it to 0? Well, if we fix it to 0, that's not going to be helpful. You may get a pred-PP error message there, but if you fix it to 0, that's not helpful, because that means the effect compartment concentration is going to be equal to 0, and that's not our goal here. We want some amount in the effect compartment so that we can estimate that time course, that shape. Fixing it to 0 would essentially shut off the effect compartment and would force us to have either a 0 observation for response or link the response directly to the central compartment. When I post up some of the practice problems, you'll see there are different implementations of that effect compartment, and I've done them with Advan 5 and Advan 6 to show you the general linear and the differential equations as well. Now here's another strategy you might take, and somebody asked the question earlier about what happens in the case where the PK model doesn't describe the PK data well. You're missing Cmax, or you're having some sort of problem describing the data. Well, if you have extensively sampled data throughout the time course of the response you're modeling, you could do something like this called a semi-parametric effect compartment, where we're going to drive the PK/PD link without a compartmental PK model. And basically what we're using is the observed concentrations to create a linear spline to represent the concentration model. So we're simplifying the PK model to just a connect the dots type relationship, but we're using that as a driving function for the effect compartment concentration. So this is a clever way to do this, and this actually was proposed by Louis Scheiner. This code comes from the old NONMEM repository, and it's pretty interesting. Now, what we're going to do here is use Advan 6 differential equation block so we can get access to the integration time t. You'll see how that works. So imagine a case here we have a single dose scenario where you have extensive sampling over time, and let's say a single dose studied over 24 hours. And you have rising and falling concentrations, and then you have similar rising and falling response, but the response is not in equilibrium with the concentration. There's some lag behind. There's a disequilibrium there, and so we want to use some sort of an effect compartment to represent that lag. But the PK model maybe wasn't performing so well, so we want to use a simplistic model that actually captures all the data. So all we're going to do is use the observed data points and connect the dots with linear interpolation. So there's one compartment in this model. So see the $a model statement here says compartment equals effect. That's it. There's just a single compartment. So $pk here is where we're going to specify the PK model. And there's a little bit of condition setting first. So new ind not equal to, that's the first row for each individual. So when you're, remember the way NMTran works and NONMEM is that at every data record, the control stream is called and predictions are made. So if it's the first data record for a new individual, this block will get executed. And all it does is initialize a couple of variables. LCP is equal to 0 and LTime or LTM is equal to time. That's initialized. So at the beginning of each individual, LCP is 0 and LTM is time. We start off then with the first intercept being 0 or LCP, and the first time of that intercept is equal to time. So that's the starting point for this linear interpolation. We're also going to find a KE0 here. That's not relevant to the interpolation. That's just for the pharmacodynamic model. And then we're going to calculate a slope and an intercept for each time point. So we've calculated the intercept. The slope then is going to be the change in concentration over the change in time. So the denominator of that relationship is time minus t int. So the current time minus the intercept time. Okay? That's the delta time. And then there's, if the time hasn't changed, we just set the slope to 0. That's just to avoid divide by 0. Else, then the slope is going to be equal to the current concentration observation, CP's in the data set, current concentration observation, minus the intercept, which was the previously set concentration, divided by the change in time. So this is delta C over delta T, or change in concentration divided by change in time. Now we can make the projection to the next time point, and now we update that the last CP is now equal to the current CP, last time is equal to the current time. So you see how this will loop over, and if you have to understand that PredPP is a recursive subroutine, so it is called from one record to the next, and it's that recursion that makes this work, because there's some memory as to what the last concentration was in the last time, and as you cycle through the concentration time records, you're able to conduct this sort of a linear interpolation. So that gives us, as we cycle through the data records, that gives us the linear connect the dots sort of model for PK. Now the effect compartment is kind of neat here in that we're going to define some input function in differential equation block, and that's going to be the intercept plus the slope times the amount of time that has elapsed in that segment of the linear interpolation. And the way we get at that is, remember, in the PK interpolation, we only have time at each data record. But in a differential equation block, we have T, the integration time, which is essentially a continuous time. And so we can see now that this input concentration is going to be equal to a prediction based on that incremental continuous time minus the last intercept. And so essentially we have an interpolated concentration across that linear segment in the linear interpolation. And that's used now as the driving function for the effect compartment. So dAdt1, which is the rate of change in the effect compartment, is going to equal to KE0 times the input minus KE0 times the effect compartment concentration. dAdt1 is actually a concentration, so it's a dCdt here. Or in other words, KE0 times plasma concentration minus KE0 times effect compartment concentration. So this is the clever trick that's used here to make that link. So this sort of semi-parametric approach works if you have extensive data throughout the entire observation interval. If you had a study, for example, that was a multiple dose study, and maybe you had extensive data on dose 1 and then continued dosing up to steady state, and maybe extensive data on dose 7, this is not going to work, because you would be missing that history of the concentration effect relationship and driving of that effect compartment concentration between day 1 and day 7. So this only works if you have a completely observed time course over the observation window with extensive sampling. But if you have that case and the PK model does not perform so well, which is often the case in early phase 1 studies, formulations are pretty rough at that point. Sometimes just powder in a bottle or some very crude formulation, which leads to all kinds of weird absorption profiles. And so this might be a nice, easy way to model exposure-response relationships that require an indirect relationship or an effect compartment when the PK modeling would be way too complex. So that's the idea for the semi-parametric. Let's talk about another variation on the theme. Here we're going to look at a simplified model for tolerance. And this is pharmacodynamic tolerance. This isn't tolerance in the differential equation block. This model for pharmacodynamic tolerance describes drug response, which is equal to some function of the central compartment concentration. So the drug response now is direct. It's related to central compartment concentration, but it's modulated by this hypothetical tolerance. And when I'm talking about a tolerance factor here, it could be any physiologic reason, some sort of tachyphylaxis or adaptation of the system. It could be development of an antagonistic metabolite competing for the same receptor, all kinds of reasons for this. We're going to view this a little more empirically, and not try to derive any mechanistic knowledge from this, but we just want to be able to describe the data. So the way that this works is that drug response is equal to slope times concentration. So that's a linear pharmacodynamic model right there. But that's modulated now by this part of the expression, 1 plus the tolerance concentration divided by EC-tol. So EC-tol represents the sensitivity. It's sort of like the KM or the EC50 for the tolerance effect. The smaller the EC-tol, the more potent the tolerance effect. K1-tol here is the exit rate constant. It serves a similar purpose to K1E in that it describes the time course of the generation of tolerance to this response. So this has been used in a few cases. Porcher et al. Used this to describe tolerance to nicotine effects on heart rate. And that's a classic paper describing this sort of relationship. It's also been used to describe tolerance to nitrates in angina. It's a pretty simple way to do this, but it does make some assumptions. One, that the response is linear, and that the tolerance response is a linear relationship to the concentration. Here's how we set it up. So remember, this picture here looks a lot like a two-compartment PK model. So we're going to use that analytical advan, again, advan 4 trans 1. The difference here now is that the data set is set up so that dV is equal to PK or PD, and there's no compartment item here because the dependent variable in both cases is driven by the central compartment. So PK observations are in the central compartment, and PD observations are also driven by the central compartment. They're just modulated by this peripheral or this tolerance compartment. So we're going to have to account for that. But the dV now is a single column. There's no CMT data item. We do have a type indicator to indicate PK versus PD. Okay, so in $PK, we're going to specify the required parameters for advan 4, trans 1, which is the microconstants, but we're going to use Ka, clearance, and volume, and then back calculate those. So K is required, Ka is required, and then the scale is required. So this is very much like the effect compartment model. We have a K-tol, which is equivalent to the Ke0. And again, mass transfer from the central compartment to this formation of tolerance has to be negligible, so we anchor that down as 1/1000th of the exit rate constant. And K32 is equal to the tolerance rate constant. Again, we'll set up this equality so that we're interpreting concentration in the tolerance compartment in the same order of magnitude as concentration in plasma. It's completely artificial. Now here's the tricky part. Now we're going to specify two different concentrations. C-tol, which is the amount in the tolerance compartment divided by the scale, and CP, the plasma concentration, which is A2, amount in compartment 2, divided by its volume. Okay, that's all fine. We specify the PD model here, which is a slope for the pharmacodynamic response. We have an EC tolerance, which is an estimated parameter. We have an E0, which is the baseline. And so effect is the same expression I showed you above. It's the intercept, the baseline effect, plus slope times concentration in plasma, divided by this modulation from the tolerance compartment. But here's the one case that we've looked at so far in this whole course where we have a single endpoint, in this case it's effect, that is now a composite of multiple compartments. We have plasma concentration and tolerance compartment in the same expression for this one dependent variable. Okay, and the reason we can do that is because we've defined them both here. And if we had some other factor in there that we wanted to include in the response, we could model that as a separate compartment as well. The key is that we've defined them and we use them explicitly in the expression here. This is one case where the F variable from the PrEP-BP routine is not going to work because we're actually pulling concentrations from two different compartments to predict one variable or one dependent variable. So that's the effect relationship. It's got an additive residual error. We have the concentration relationship and then the indicator switching between the two, just like we've been doing all along. Okay, but the key here is specifying the compartment concentrations for each component of the model. And that allows us then to define this relationship, which is a function of both central and tolerance compartment. Okay, let me answer a few questions now. Question is, if all the PK points overlap with PD time points, will the semi-parametric effect be necessary? Well, if we say overlap with PD time points, I guess what you're saying is that there's matched pairs. Each PK time point is matched with a PD time point. Yeah, a semi-parametric could still be required there because you could have the peak of that response or the kinetics of that response could be quite different, even though we have matched pairs. You know, that's what we see in a hysteresis plot and so on. So it doesn't matter if the time of the PK/PD are matched. What matters is, you know, where does the pharmacokinetic relationship peak with respect to time versus the pharmacodynamic relationship. So there's this equilibrium between the distribution of effect and concentration. Okay, somebody's asking why don't we code it that K32 is negligible? Why isn't it K32 instead of K23? Well, because we want the transfer from central to tolerance or from central to effect compartment to be negligible. The whole key here is we don't want to affect the mass balance of the PK system, which is the first two compartments. So we've got to cut it off right here at this transfer. So making this negligible prevents any impact on the central compartment concentration. If we didn't do that, if you made this transfer back negligible, well, we could still have distribution to the tolerance compartment, and that's going to mess up your entire PK system. So what you want to do is isolate the PK system by making the transfer from central to effect compartment or central to tolerance, making that negligible. That's why we do it at the K23 here. Okay. All right. Next topic is more on indirect relationships, but a different mechanism for modeling them. The indirect pharmacodynamic response models. And the key here is that now response is not some prediction that is the function of a compartmental concentration. Response is actually an observed compartmental concentration or amount. So the response is described as the quantity in that compartment. And the way the drug effect is mediated is by either inhibiting or stimulating the formation or elimination of the response. So, for example, we have a response compartment now, which is formed by some zero-order rate constant Kn and eliminated through a first-order rate constant Kout. And we could describe the rate of change of the response over time at steady state or under constant conditions where that rate is equal to 0 as something like this, Kn minus Kout times R equal to 0. If Kn minus Kout times R is equal to 0, then we can solve for the response at baseline or time 0. And that's just simply the ratio of K in to K out. So R0 here is our baseline response. K in is the formation rate, and K out is the elimination rate constant for response. And what we're looking at in this expression is a response that's constant over time. Well, let's talk about how we implement a baseline response in NONMEM. There's a couple of ways to do it now, since NONMEM 6. But I'll teach you the old classic way, as well as a newer shortcut. So R times 0, R0, is equal to the ratio of K in to K out. We just explained that. What we could do then is to set the initial conditions for the differential equation compartment. Remember, NONMEM doesn't, in the differential equation block, allow you to specify initial conditions. We can do it through the data set by dosing into those systems, and so that's what we're going to use. We can also do it by using the A0 parameter, which I'll show you in a minute. But let's do it through the data set. So we initialize the amount in the data set with a unit dose, so just a dose of 1 to the response compartment. Let's call it compartment 3. So if R0 is the response at baseline, then how do we have to scale the dose of 1 here to achieve that? Well, one way to scale a dose is by multiplying it by some bioavailability fraction. That's a reserved parameter in a PK system model in NMTran. And so we can estimate F3 as a scaling factor to multiply the initialization of unit dose 1. So F3 times 1 is going to give you your baseline. Well, we said that the baseline was equal to the ratio of K in to K out. So F3 then is equal to the ratio of K in to K out. And that gives us our response at time 0. We can model K in and K out as fixed and random effect parameters. Oftentimes it's very difficult to estimate inter-individual random effects on both of these unless you have extensive data and drug effects on one end of the system that are quite pronounced. But you could try to estimate the individual random effects. So that's how we'll set up this idea in the models we're going to look at, where we're going to use a dummy dosing record to initialize the compartment and scale that dose of 1 by the bioavailability fraction. Well, alternatively, in NONMEM 6 and 7, there's a new method that allows you to initialize the compartment directly. So we can specify A_0, so that's the amount, the initialization amount, and in the parentheses we'd specify the compartment number. So A03 is the initial conditions for compartment 3. I'm going to set them equal to base here, and base is a parameter that's a function of K in and K out. So that does the same thing as we described above, except it does not require the insertion of dummy data records at time 0. Okay, so we can estimate initial conditions directly without initialization data records by using this method. Okay, well, as you know, there are many different variations on this theme of indirect pharmacodynamic models. And these indirect pharmacodynamic response models can be difficult to distinguish between different cases. But I'm going to show you all of them and some code for estimating these. We'll scroll through each one of these. So let's look at the first, inhibition of formation. This is one where the drug effect works on K in. And in fact, the drug inhibits the formation rate. This is a zero order rate. So dRdt is then described by K in times some inhibitory Emacs function minus K out times response. And what happens there, if we inhibit the formation, you'll see a drop off of the response over time and then a return to baseline after the drug effect wears away. So the estimated parameters, and it could be fixed here, but Emacs would have to be bounded at a value of 1. You can't have more than 100% inhibition. And then the IC50 here would also be estimated. Here's another one where we have inhibition. This is inhibition of the offset. So we inhibit the first order rate constant K out. And so now the expression again is the zero order input minus the first order output times this inhibitory expression. Again, Emacs has to be constrained to be between 0 and 1 because you can't have more than 100% inhibition. But by inhibiting the exit rate constant, what you end up with is a buildup of that response or the response mediator over time. And then, of course, as drug concentration comes back to 0, this response drops back to baseline. The next is a stimulatory indirect PD response model where drug is stimulating Kn or stimulating the zero order formation of response. And I just noticed here we've got a typo in the translation when we moved over. This relationship here is a change in response over time where Kn is multiplied by a stimulatory Emacs model. So this should be 1 plus Emacs times C divided by EC50 plus C. I'll correct that and post. Where we can modulate Kn by increasing it as a function of drug concentration. And by increasing Kn, you see an increase in response over time and a return to baseline. And then we can also stimulate the offset. When we stimulate offset, of course, we're going to rapidly eliminate the response or the response mediator. And that's modeled, again, another typo here. Sorry about that. Kn is the zero order rate constant minus K out, the first order, times 1 plus this stimulatory Emacs effect. If we stimulate K out, we're going to see a drop in response with drug concentration and then a return to baseline. Okay, so those are the 4 classic indirect pharmacodynamic response models. There's all kinds of variations on that theme. But let's look at the implementation for one of those. This is the indirect PD response model. Actually, I think I've got them all here, so we'll look at them quickly. We have in the input here, very similar to the effect compartment model, where now we have type and compartment. Compartment is indicating the response compartment, and in compartment 3, and PK observations in compartment 2. Compartment 3 in this example was initialized with amount equal to 1 at time 0. So we're using the old method where we're going to use F3 to scale. So we have a subroutine Advan 6 differential equation model. Trans 1, tolerance equals 3. Tolerance 3 is a good starting point. You might need to increase that depending upon numerical integration difficulties. 3 compartments here, gut, central compartment for concentration, and the response compartment. So we can define a PK model just as always with a Ka, clearance, and volume. These are not recognized variables, but we'll use them in the differential equations. And where K here is the exit rate constant. The PD model parameters, we have a Kn, that's the zero order formation rate constant. We have a K out, which is the first order elimination rate constant. We have F3, which is defined as the ratio of Kn and K out. F3 is equal to R0, baseline response. An Emacs and an IC50. Then in the differential equation block, we define concentration in the central compartment because that's our drug effect, our drug source. And then the effect relationship is equal to Emacs times that concentration divided by IC50 plus that concentration. So these parameters are estimated. They're components of the PD model, but they're indirectly related. And you see down here that we have the typical mass balance for the gut and central compartment. When we get to the response compartment, we're going to modulate Kn here by inhibiting it 1 minus E. E is this Emacs relationship here. And that allows us to inhibit K in. K out is not modified. The way we model the error block is the same as, well, similar to what we usually do, where CP is A2, and so concentration is equal to CP with some residual error model. Effect now is just directly what's observed in compartment 3. So we don't need a PD model here. The effect is equal to the response compartment plus some residual error. We still switch between the two different types because this is a simultaneous fit. Okay, so the key thing here is that effect is equal to an amount or a concentration in one of the compartments. It's not necessary to scale that or multiply it by some slope or Emacs relationship. One of the keys here, though, is in the initial estimates. I left that in here. We're fixing Emacs equal to 1. So we're assuming this drug can exhibit 100% inhibition of Kn. If you don't fix Emacs to 1, you certainly have to bound it at an upper end of 1 and a lower end of 0, because you can only inhibit 100% of that rate. So this is equivalent to that first model we talked about, the inhibition of Kn. One question here that I'm going to answer is about the initialization. Can we specify A0 for a particular compartment or the initial amount for compartment anywhere, or does it have to be in a specific code block? Yeah, usually you'd specify it in the PK block. Okay, so A0 for compartment 3 would be specified in the PK block, so that you need to initialize the differential equations. That PK block is used to set those initial amounts. Okay. So let's look at another example. So the inhibition of K in is the first model. Then the next one is the inhibition of K out, and I'll just scroll right to the differential equations. Same sort of thing happening here, except now we're placing the drug effect right here as an inhibition of K out. This causes an opposite effect, so if you inhibit K out, you actually have a buildup of the response mediator over time, versus if you inhibit K in, you have a decrement of the response over time. So they're both inhibitory, but they're on different ends of the system. Next one would be the stimulation of K in. And stimulation of K in allows to build up more response more rapidly. So you're stimulating the formation of this response. And in that case, you don't have to bound E at 1, because you could have maybe more than 100% stimulation. You just can't have more than 100% inhibition of a particular response. And then similarly, we can stimulate K out, which would lead to a rapid decrement in the response. So those are the 4 basic variations on the indirect pharmacodynamic response model. A couple of thoughts on that. One is that if you have a data set with an indirect relationship, sometimes it's almost impossible to determine whether or not you should stimulate K in or inhibit K out. And both of those will give you a similar looking profile. If you have very extensive data, you'll see that the one is a 0 order effect and the other one's a first order effect, so you can discern some slight differences. But oftentimes we end up picking the model based on some known or assumed mechanism of action. So we might understand where a drug works. For example, if you had an acetylcholinesterase inhibitor, and the response that we're looking at is a muscarinic response or a cholinergic response mediated by acetylcholine. Well, the mechanism for that drug would be one where we would inhibit the metabolism of acetylcholine. So in other words, inhibit K out. You might consider other situations where we're actually stimulating the production of some response mediator. Okay, let's answer a few questions, and then we'll move to the next topic. So a question to explain more about the why the baseline condition R0 is equal to F3. Let me just go back to that. I'll spend a couple of minutes on that. Remember, F3 is being used as a method to scale the initialization amount for compartment. It's a bioavailability fraction in pK terms, but we're not talking about pK here. We're talking about initialization of a compartment. And if we initialize a compartment with a unit dose of 1, the fraction that multiplies that at time 0 would then result in a quantity that's equal to the baseline. So we know that F3 is a fraction that multiplies every amount inserted into a dosing record. We can use F3 then as the estimate of that R0, that baseline time point. It's just another way to initialize the compartment. In NONMEM 6 and 7, we can do it directly through A0. Okay, another question. I have a case when the PD line was flat for 6 hours, then a sharp increase. How do you implement that lag time in an indirect model? A lag or transit compartments, etc. Okay, so I understand. So relative to concentrations, which I imagine were rising and falling, initially, there's a pharmacodynamic response which is very flat, and all of a sudden a sharp increase after some period of time. So it appears like there's some sort of almost a zero lag time. Now you could do that with an indirect response relationship. You might have a very slow onset, or you might have a sequence of indirect response compartments where you need some sort of a transit. It depends upon the sharpness of that relationship. You might be able to do it with just one compartment. That's one that would be you'd have to look at the individual data set to determine. Okay. Next topic. We really didn't have a place to fit this, but it sort of fits with modeling direct and indirect PD relationships. But it's one where the baseline is not a constant. So all of these models here, we've looked at either an E0 parameter estimated as a constant baseline, or a R0, which is a constant value in the indirect pharmacodynamic response. And of course, you could always have time-dependent baselines. We can model, for example, the progression of disease as the time-dependent baseline and have a drug effect on top of that. We'll have a whole session on that later in the course. But what we're talking about now are endpoints that vary with a relatively fixed pattern. And to be specific, we're talking in this implementation about a pattern that's fixed over a period of 24 hours or less. And so we know that many physiologic processes demonstrate this sort of pattern of rising and falling over the course of a day. Endogenous release of different hormones, cortisol, melatonin, etc. Heart rate, blood pressure, QT, these all follow some sort of pattern. And whether or not, whatever the cause is, we're not going to define here, but what we do know is that there's a rising and falling of these effects within the time course observed. So if we assume that this variability is just some average intercept or some average baseline, it could really bias the estimates of the drug effects. And so modeling that pattern is important when we want to differentiate drug effects from natural variability. So oftentimes this is called circadian rhythm. Sometimes it's not always circadian. Circadian rhythm has a specific meaning of something that happens on a daily basis in a 24-hour cycle. But we can sometimes use circadian models to approximate other time-dependent shifting baselines that follow some pattern over an interval of time. Well, here's the general function for circadian rhythm. You have a circadian rhythm equal to, or the circadian baseline equal to some amplitude times a cosine function. The cosine is pi squared times the quantity of time minus the acrophase, or this is the shift in that time peak. So it might be shift from the starting point to time 0 or wherever this cycle starts, divided by the overall period. So what's the period of the entire cosine wave? It might be 24 hours, for example. We can estimate that. And if you have complex problems, you can have more than one oscillation function. So a couple of different circadian oscillations that you sum up over time. That gets kind of messy, and you have to have pretty exquisite data to be able to estimate those. But that's been done before, and there are publications that describe that. So let's look at an example. We'll use heart rate as our endpoint. And we know that heart rate changes with some within-day variation. It's slower while you're sleeping. It gets more rapid during the course of the day, and then it slows off as you go back to sleep at night. We know that drug A is a drug that decreases heart rate in a dose-dependent manner. So in order for us to assess that concentration-response relationship for drug A and heart rate, we have to account for the circadian variation in the baseline. You've got to get the baseline right before you can estimate the drug effects. Now, one of the ways to do this is to construct your study design such that you have maybe individual specific crossover or an individual specific baseline, and you can observe the pattern of variability in a subject on a baseline day, and then have a treatment day, and then just subtract off that baseline pattern. This is called a time-matched baseline. It's done all the time in QT exposure response analysis. But maybe we're not that lucky. Maybe we don't have completely time-matched baseline. We know that there's some pattern, though. And so we're going to have to develop a model to describe the baseline fluctuation. So in this example, heart rate was collected in 20 subjects on 2 different occasions. There's circadian variation in the heart rate baseline. Drug A increases that dose dependently. And so to assess that relationship, we're going to account for this. And we have a pretty rich sampling design. We have 11 to 30 samples per subject, 20 subjects each, 20 subjects in this data set on 2 different occasions. And the second occasion, so the first occasion is done in the absence of drug A. The second occasion is done after drug A is administered at different doses. So pretty good study design here, where we have baseline data and we have drug effect data. When we look at those data by occasion, blue is occasion 1, pink is occasion 2. We can see, there's some differences here between occasions across individuals. Quite a bit of variability. Occasion 2 just happens to be associated with the drug effect, and you see that the higher responses are apparent in the pink here. And there's also different doses with a dose-dependent increase in heart rate. Here we look at each individual, and you see the 2 occasions. You see a nice, clean separation in most cases of the of the baseline day and the drug effect day. Some individuals have a small or almost negligible response, and others a little bit more robust. But this looks pretty typical for a circadian type baseline with a drug effect. Now, of course, these are simulated data, and they're a lot prettier than you'd have in the real world, but it gives you the basic idea. So if that's what the data looked like, how would you model that? The challenge now is to first set up a baseline that changes over time. And we're gonna assume this particular design, which was extensively sampled. Look at all the data points that are sampled here, extensively sampled. So time in the data set is a small interval of time. The incremental observations are done quite frequently. So time in the data set is going to approximate a continuous time here. We have occasion, which identifies the drug treatment occasion from the baseline occasion. We have dose, which is a covariate as well. So we're just going to use a $pred model for this one. We don't have a PK system model to worry about. And remember, we're using dose. We could have used time-matched concentrations to drive this as well. We're going to use dose to drive this one. And so let's set up the parameters of the model. We have an amplitude and an acrophase. Remember, the amplitude is the magnitude of that circadian wave, and it's going to differ between individuals. The acrophase is the offset from time zero as to where the cycle starts. Again, that's going to differ between individuals. Pi is defined here, or 2 times pi. We have this first component, OS1, which is the oscillator for period 1. That's amplitude times cosine times pi times time minus the acrophase divided by 24, which is the period. 24 is fixed here. It's not estimated. We're assuming a fixed 24-hour cycle. Now we have some heart rate modulation here, HRM. Which is going to be estimated theta 3. We have a dose effect on that, theta 4. And we'll have an occasion-specific variable which allows us to define the effect. So if we're at occasion 1, dose is 0, right? And so the effect is just equal to some scale here of heart rate on, or some heart rate scalar here multiplied by the baseline. If we have drug treatment, we're going to increase that effect by some dose-dependent relationship. And so we're going to shift now this scaling factor by a proportionality equal to the dose times slope, where slope is an estimated parameter. And that's going to be the effect prediction. Okay, and then so we're using if-then statements. Then the observed data are going to equal to the effect. The effect just takes on different predictions based on these occasion if-then statements. So this is a simplistic way to get that sort of oscillation in place. We're assuming a period of 24 hours. And we're just allowing that baseline oscillation to be scaled according to drug effect. And those are the observed data, but the simulation model used the same sort of structure. And you see here pretty closely in sync. We have the baseline and the treatment day. Now, you could imagine a case where maybe there's a slight shift in the acrophase on those 2 different occasions. That becomes a very difficult problem to identify because remember, your drug effect and the circadian pattern can be confounded in the treatment day. So you really need to make some assumptions that the pattern is similar on both the baseline and treatment days. But in any case, I wanted to show you how we can model a more complex baseline. You could apply this to any pharmacodynamic model after describing this baseline. You could have any sort of pharmacodynamic model on top of that. Okay, any questions on that? Do we assume the same circadian pattern for all subjects, or would you allow random effects on shift or amplitude? Yeah, you can. I think what's important to assume is the same circadian pattern on the two occasions within subject. But we could have a random effect on amplitude and shift here. The starting time of the function will affect ACR1. Should this be controlled? Yeah, that's right. So we're assuming a starting point starting at 0, but with an estimated acrophase. So that's going to be an offset there. And so that's actually estimated as part of the model. Okay, any more questions? Well, I'll give you another minute to ask questions. I'm going to talk about the assignment for this week. Since this is a review session, we will do a lab on Friday that illustrates some of these, and I'll post that up to you today on the website. The examples are going to be based on indirect response, an effect compartment model, or an indirect pharmacodynamic response model. I will also assign some reading for next week, 2 or 3 articles that would be helpful in preparing for next week. They're not mandatory. And I'll post those as soon as we get out of class today too. Besides that, just make sure you're familiar with these concepts, particularly the indirect pharmacodynamic response models, because that's really the starting point to branch out to so many different extensions in pharmacodynamics. So we're going to talk about precursor pool models. We'll talk about lifespan and transit models, models for multiple endpoints in a turnover type configuration. So all of these are based in that same sort of structure. So it's important to get the basics down today. Okay, so a few more questions have come up. Let's see. Oops. So there's a question here about relating K23 and K32 to K1 on page 70. I think I have the wrong page here. Page 73, sorry. Can you relate the K32, K23 in the model to K1 tall in the figure? Yeah, sure. So K23 is K1 tall. K32 is this K1 tall. Or I'm sorry, K tall 0. And so what we end up with is K23 fixed to some negligible mass transfer, and K32 is estimated as the K tall. Just like the effect compartment concentration. So somebody's asking about explaining why we can use Advan 4. I'll spend another minute on that. I don't I still don't understand why K32 can be used for KE0. Okay. Well, here we go. Advan 4. Let's go back to the effect compartment model. Advan 4 is used. Remember, Advan 4 is the 2-compartment model. So the required microconstants are K23, central to peripheral, and K32, peripheral back to central. But we're modeling something that looks like this. A K23 and what looks like a K30. But the point is, it doesn't really matter. If the return rate constant is K32 instead of K30, it doesn't matter because K23 is so negligibly small. If the amount returns back to the central, it's a negligible return. If the amount is eliminated here, it's a negligible elimination. So it's really arbitrary. You could have this rate constant going anywhere because K23 is really what controls this, and K23 is not impacting the mass balance of the central compartment. So that's why we can use Advan 4. We can say we'll fix this transfer K23 to some negligibly small value. But the return rate constant will not impact the mass balance if we return it to compartment 2 or if we just exit from compartment 3. It doesn't matter. That's why we can use Advan 4. And then the follow-up question, if it's negligible, then how is K32 identifiable? Well, remember, it's a negligible mass transfer. Okay, the mass is negligible, but we scale the compartment here, so no matter how small that mass is, if we have a small enough volume, the concentration here in the effect compartment could be important for at least defining the time course. So KE0 is still identifiable, or K32 here, it's still identifiable. It's just that it's not impacting the central compartment concentration. And remember, we set up that equality so that we're scaling these so that they're in approximately the same order of magnitude, central and effect compartment concentrations. So just because there's a small mass in this system doesn't mean it's a small concentration, because of course concentration is equal to mass divided by volume. All you need is a small volume to adjust for that. So that's the trick we play here in order to have negligible mass transfer but an observable concentration time course in the effect compartment. When should we use the model with tolerance? Well, tolerance is a scenario that you would observe where the hysteresis loop actually becomes a clockwise loop, where the response at an early time point is at a given concentration is greater than the response at that same concentration at a later time point. So there's some sort of inhibition of the response or some tachyphylaxis that causes a reduction in the response at the same concentration. So diagnostic for that is a clockwise hysteresis loop, also known as a proteresis loop. If you're not sure, read that paper by Porcher et al. That's a nice description of that sort of phenomenon. You can comment on the comparison between effect model and indirect model in terms of computational difficulties. Well, you know, the indirect pharmacodynamic response model is a differential equation model, and that does lead to some complexities because you have a numerical integration going on, whereas in the other case we have an analytical solution. So there is that complexity. Runtimes are slower with the numerical integration of differentials than they would be of an analytical solution. So that's another issue. If you have the choice and you don't need to move to the differential equations, use the analytical solutions. Sometimes you're not going to have much of a difference in the predictive abilities, whether you use an effect compartment model or an indirect response model, particularly if it's just single dose PK/PD. Okay, I think that wraps up the questions. As I mentioned before, we've got a couple of typos in the handouts here that I'll fix and post, and I'll also post your assignment But we'll pick up again on Friday with a demonstration of the effect compartment models, and we'll speak again then. Meanwhile, if you have questions, feel free to post them to the discussion boards. Thanks everybody for your attention today. We'll talk again on Friday. Enjoy the rest of the week.